dedicating his time for the professional development. It's much appreciated. I don't see anybody else in Pakistan, at least, doing such a professional work. You know, most of the people are interested in their business, but very few are paying attention to the professional work of the civil engineering and particularly geotechnical engineering, which is the most difficult part in engineering because everything is below ground. We can't see anything.
No, Shahid Sahab, totally agreed. It's a wonderful job, jo Tahir Saab and people of his like, particularly I miss Mirza Saab's, Rizwan Mirza Saab's presence here a lot. Allah Ta'ala unko sehat de. So these people, the role of these people is more like a wicket keeper or a goalkeeper in sport. It's a thankless job. You never realize their importance jab tak, till the time anything goes wrong. So I think it's
Sorry,
wonderful.
Dr. Saab, विकेट कीपर
So
या
here
गोल
it is
कीपर
now.
नहीं, ये they are everything. They are वो अंजुमन है, अपनी जात में अंजुमन है ये. आप एक तो
Thank
कैसे
you
कह
for your
सकते हैं?
kind words, gentlemen. Thank you for your appreciation, your kind words, realizing how thankless job it is. But inshallah, alhamdulillah, and I'm not alone in it. The credit doesn't go to me. The real credit goes to the team, the whole team, the founder members, and especially my what should I say to him? He's more than a brother, Rizwan Mirza. He has laid a very solid foundation of this society. His contribution is priceless. His contribution is enormous. And I don't have words how to describe how much hard work he has put in this society, whether it was our publications, whether it was our lectures, I mean, in every field required for this society, he worked day and night. Let's pray to Allah to give him health and recover from the present situation. And he should recover as is possible from his current situation. Thank you very much for your. So now I am going to start it formally. We are now live on Facebook also. And now I'm going to start it formally. In the name of Allah, the most gracious and the most merciful. Somebody interrupted. Okay, Bismillah ar-Rahman ar-Rahim. In the name of Allah, the most gracious and the most merciful. Ladies and gentlemen, Assalamu alaikum and good afternoon from the Pakistan Society of Civil Engineers. We warmly welcome all participants, including those joining us on Facebook. This is lecture number 84, part of our monthly series that has been ongoing since 2020. Through these lectures, PSC aims to provide both young, emerging, and experienced engineers with the latest knowledge across various civil engineering disciplines. Now, before I introduce the guest and the topic, PEC requires me to read the rules of this webinar right from the start. So the rules are: all registered participants for CPD points have to appear live on webcam. However, for the ladies, there is an exception. If they wish, they can cover their face while appearing live on the webcam. During the lecture, microphone of all the participants except that of speaker shall remain in mute position. At the end of the lecture, there will be a 20-minute question and answer session. And that session for the questions, all questions have to be typed in the chat box only, and I will read the questions, and inshallah, our guest speaker will answer those questions. I would recommend that during the lecture, you should keep on typing your questions wherever you feel you have to ask a question. And I am there, I am monitoring all the questions. If it is a question which is to be asked on a certain slide, and it is a pertinent question, inshallah, I will ask Dr. Sai I'll interrupt him, and I will inshallah ask him to answer the question. And he will be very pleased to answer that question at that time. Participants on the Facebook have the same option. They can also type their questions in the chat box, and inshallah, we will Dr. Saab will answer them. So, ladies and gentlemen, today's topic is practical insights from load testing of drill shafts. And our guest speaker today who is no stranger to PSC. I think it is his third lecture here, but still I'm going to introduce him. Our guest speaker is Dr. Muhammad Irfan. Dr. Irfan earned his undergraduate and master's degree in civil engineering from UET Lahore in 2008 and 2011 respectively, before pursuing a PhD in geotechnical engineering at the esteemed University of Tokyo, Japan. A highly accomplished geotechnical engineer, Dr. Irfan specializes in foundation design and optimization, touring systems, and tunnel engineering. His extensive experience in geotechnical investigations includes a strong emphasis on slope stability and landslide early warning system. He is also adept to applying finite element modeling to resolve complex geotechnical challenges, ensuring both safety and efficiency in demanding environments. With 16 years of professional experience and 19 publications to his credit, Dr. Irfan brings a depth of expertise and a pragmatic approach to the field. He currently leads his own consulting firm in Pakistan, delivering advanced geotechnical solutions across a range of projects. His academic and professional trajectory reflects a steadfast commitment to the advancement of geotechnical engineering. Dr. Saab's professional affiliations are naturally with Pakistan Engineering Council, then Japanese Geotechnical Society, and then he also is a member of International Society of Soil Mechanics and Geotechnical Engineering, Japanese Society of Civil Engineers, and Pakistan Geotechnical Engineering Society. So now I invite Dr. Irfan to please take the floor and start his lecture. Dr. Saab, start please.
Thank you very much, Tahir Saab, for the kind introduction. I believe my screen is visible. If you can just confirm that, and if I'm audible, then I'll begin. So, Tahir Saab, is my screen visible and am I audible, I believe?
Yes, your screen is visible. Mashallah, your voice is also okay. Thank you.
So, thank you very much, Tahir Saab, for the kind introduction. And I'm gonna continue on. So today's discussion topic is beyond the numbers. It's more on the practical side. There might be a lot of things that we don't find in the textbooks. And there are certain things that we often don't even discuss them. So the objective of today's discussion is to look from the hands-on perspective, how the load testing of the drill shaft is to be, what are the pitfalls in that, which needs to be avoided, and how these can be implemented for for the estimation of the pile performance in a better way. And just to set some context, this is the third lecture in the series, which I've been honored to be invited by PSCE for the third consecutive years on this. In 2023, when we started, we talked more on the design and the construction of the pile side. So that's something we discussed back then. And then last year, we talked more on the load and the integrity testing of the pile. That was more of a generic in nature, where we discussed about different kinds of load testing and the integrity testing, different techniques on that. And based upon a lot of questions that we got from last year's lecture, I realized that there is a lot of interest in the engineering community about the load testing, particularly the static load testing of board piles. That's something which is quite common in Pakistan as well. And even if we talk about the Middle East and other industries, so that's the board piles are mostly the common technique adopted. So that's why I decided to focus this time more on the load testing and more precisely on the static load testing of the drilled shaft. So that's going to be the focus, and that's going to build on the previous discussions that we've had over the years. Now, the first question is why it's even important to talk about the pile testing. Why pile testing is important. So this picture that you'd see in front of you, just try and make a guess what would have led to this kind of a situation. Some of you might think that the driver might have been quite careless in his approach and he would have just driven something on top of some pole which is extending from the ground, or some movable things underneath. But you can make all your guesses, but probably this is the last thing that you would have expected, as I can show you in the next picture. So what actually happened was it was a driven pile which was being driven on the opposite side of the road. And this pile underneath it bent and bent, and there was a car on the parking lot on the other side, and it just lifted it up. Now, that's the nature of the problem that we are dealing with. Piles are hidden structures, and their failures can be very costly. So, if there are any construction errors, there. So it's important to understand that more often than not, it's a construction errors which are there, and less common are the design errors. So design errors are generally less frequent than the construction errors because of like this example that I've shown. And you can see that there are a variety of construction problems that you can find in case of piles. Just see all these pictures, and maybe if you have this kind of a defect, which is at a shallow depth, probably an easier solution is that you excavate around it and you can fix it. But you can imagine if this kind of a thing happens deep into the pile, it's very difficult, or rather pretty impossible, to actually fix it. So this is where pile testing comes in. This is where pile testing can be of help for us. So testing shows us that both the quality of construction is up to the mark, and it also enables to validate the design assumption. So that's the challenge, and that's the benefit that the testing gives us. Now, what our ultimate goal is? Our ultimate goal is to have a good pile performance. And what testing does is that it provides us with a feedback loop between the design and the execution things. What I mean by this is, in order to make you better understand that, let's look at the geotechnical design cycle. Now, talking about the geotechnical design cycle, we know we start with the geotechnical investigations. And when we talk about geotechnical investigations, our main goal is just two things. We want to determine the lithology, and we are interested to determine the strength of the soil. So these are the two things that we are mostly interested in. Then once we have done geotechnical investigations, we have determined these two things, then based upon the lithology and the soil strength parameters that we establish, we design the pile. Now you design the pile, what we mean by that is we are generally talking about establishing the pile diameter, the length of the pile, the center-to-center spacing, the group efficiency factors, and things of that sort. So we design the pile like that, and then afterwards, what the next step in the geotechnical design cycle is, because these piles are supposed to support very important structures, the next step is that you have to verify your design assumptions. So you have to validate your design. For that, generally the codes and the standards suggest that you cast an index pile or a test pile, and you load that pile, put like the real world conditions on top of it. So you load it 2 to 3 times of the design load, and you see how the behavior is. That's the objective, because we ultimately are looking to validate the performance. So the behavior or the performance of the pile, since it's going to be a very important component of the structure, you need to validate that. And then once you have done design verification, then you go to the working piles. Once this thing is cleared, once this thing is approved, then you go to the working piles. And then in the working piles, again, once you construct all the working piles, you're still again required to check the integrity of the piles and the load carrying capacity of the piles. And what this kind of testing helps you doing is that it pretty much closes the feedback loop. So you see, in this, these two are pretty much like the design phase things. The geotechnical investigations and the pile design, that's the design phase thing. Then this is the pre-construction stage, and ultimately this is the construction stage. What I mean by that is, so this is a very important and a critical stage that we call as a pre-construction stage. Now, what happens in this stage is it sometimes is mixed with the construction stage because of the short time span that you would have. But our today's focus is mainly going to be about this pre-construction phase, the pile testing that is done as for design verification. So that's going to be the main goal of our today's talk. So once you have done all that thing, then what this testing on the working pile does to you is it pretty much closes the performance feedback. It provides you the feedback that, okay, you made all these assumptions over here. And after making all these assumptions, you validated these assumptions like this. And from these assumptions, you ultimately completed your construction. And is this construction according to the design assumptions or not? So that's what this feedback loop tells you. So another important aspect to note over here is that the type of testing that is required in the pre-construction stage and the construction stage are different. The objective here is mainly to determine the performance of the pile. So that's why most of the times it's the load testing which is required. And in this stage, yes, loads testing is just like a verification of the design assumptions, but at the same time, you need to check whether the integrity of all the constructed members, that is the piles, is appropriate or not. So that's the thing that we are talking about here. So by doing all this, what we are actually trying to do is our ultimate objective is to assure the quality of the pile, if it's good or not. So now let's see, what do we mean by pile quality? Now, talking about pile quality, we need to see that if we are to assure the quality of the pile, there are two questions that we need to answer. Our concern is to assure the quality of the pile. We need to see what we need to check. And the second question is how to check that. So to answer the first question, what we need to check, it's basically the two things. One, as I already mentioned, it's the integrity of the pile that we need to check. And the second thing is the load carrying capacity that we need to check. So if you just confirm these two things, you've pretty much answered the question whether the quality of the pile is good or not, because that's the question that mostly we engineers are required to answer, whether the quality of the pile is up to the mark or not. So just by answering these two questions, that whether the pile integrity is okay and whether the load carrying capacity is okay, we can answer this question. Now, talking about integrity, since it's a slightly different word, it means whether the pile length is appropriate, whether the cross-sectional area is okay, are there any cold joints or other cracks within the pile, or is there any segregation of concrete? So that's what we mean by pile integrity. Now, how do we check it? In order to check it, there are different methods which are used. For example, some of them are listed here. This is just some of them. And as I mentioned earlier, I've discussed them in more detail in last year's talk. So I'll not touch upon those today. So today, for the load carrying capacity, we can perform the static pile load testing, the high strain dynamic pile load testing. There is bidirectional testing. There are some other techniques like the statnamic and others, but that's something that I'm not going to go much into detail today. So our today's focus is going to be on these two topics mainly. First is the static pile load testing. That's something that I'm going to look more deep into it and more from the practical aspect. And this is a very new and innovative technique. And I'm sure people here working in the Middle Eastern industry would already be aware of that, but that's something that's not common in the Pakistani construction industry. So I'm just going to give an overview of this bidirectional pile load testing. So that's how I'm going to frame today's talk. So what I'll do is, with Tahir Saab's permission, that I've tried to structure the talk in a way that I've divided it into two parts. So the first half I'm going to cover in an hour or so, and then we can have a break and we can answer the questions that you'd have in this first half, and then we can move on to the second half. So going forward, so let's talk about the pile load testing. So just to give you a quick overview of what static pile load test is, this is how the assembly looks like. What you do is you place a hydraulic jack in between the pile, which is here, and a heavy reaction load at the top. And when the jack tries to expand, because of this heavy load at the top, the jack cannot go up, and as a reaction, the load comes down on the pile. So that's how this works. So that's how you are able to put load on the pile. And although I've talked about this reaction assembly, that's the big concrete blocks or soils that you've seen on top of the pile. There are many other types as well, and that's something that we'll talk more in this lecture. So we've performed the test, and once we've performed the test, the question is, what's the test output? So after performing the test, what is the output? The output is a single graph that we are generally aware of, and that's something we call as a load settlement plot. Now, what I mean by load settlement plot is, let's look, this is how typically a load settlement plot looks like. And then after performing that static pile load test, all our discussion is focused generally on this load settlement plot. So that's what the focus of our whole discussion is about. So as we started, that our ultimate goal is to have a good quality, to understand the pile performance. And since this test is a very important component, so if we are to perform a high quality pile load test, what are the things that we need to measure very precisely, very accurately, to be able to say that the quality of the test was very good? And because the quality of the test was very good, that's why we are very confident of the pile behavior that we understand. So, so the question is that if we are to have a reliable test, what are the things that are required? And you would see from this graph that there are only two things that we are concerned about. We're only concerned about the settlement, because this graph only has settlement on the x-axis. And the other thing we are concerned about is the applied load. So only if we are able to measure these two things very accurately and precisely, that is the head settlement and the applied load, we are able to get a high quality test. But it's easier said than done. So in the next slide, what I'm going to do is I'm just going to show you the examples and problems from the practical angle, which can occur in the determination of a high quality pile head settlement and also the applied load. So what are the biases?
Dr. Irfan?
Yes.
Little interruption. I just want to inform you that a lady from China, she manufactures O cells, I think probably you also know her. She has also joined us, and she is listening to your breakfast. So thank you very much, Shia, for joining.
Okay, that's
Please
good to
go
know.
ahead, Dr. Saab.
Thank you.
Hi, hello everyone. Thank you for letting me join this engineer meeting. Hello.
Thank you, Shia. We have heard.
Thank you.
Let Doctor continue, and later on after the lecture, maybe we can have a little chat. Thank you.
Yeah, sure.
Okay, so what are the biases in the pile settlement? In the pile settlement, there are so how do we measure the pile settlement? We measure these pile settlements. Basically, there are reference beams that we put in. We put in gauges on top of it. And that's how we measure the pile settlement, the head settlement. So what biases can be there? There can be unstable supports of these reference beams. This end supports can be a little unstable, and because of the movement of those, because of the movements of those reference beams are ultimately obtained settlement values would not be so accurate. And at the same time, there can be some environmental effects, because of which you can see it's generally covered, as the ASTM standard suggests, to protect it from the environmental factors. It's protected. And so these are some of the common problems. And also what happens is that in the cartilage arrangement, as I've shown here, generally speaking, the space is very congested. And because of that congested space, it's often very difficult for people to actually go in and take the readings from these dial gauges. So obviously one way is that you get the digital data acquisition, but that's something which is not very common locally. And the other way is that you can just put CCTV cameras there and get the reading. So that's another a simple way out of it. If you don't have the digital sensors, although that's something which should be which is something that should be encouraged. And also, as I was just mentioning, that the human errors can cause a lot of problems in it as well, because these dial gauges are so small, and sometimes because of wind and other factors, it's difficult to read the readings. Sometimes dust goes on the surface, and it's difficult to read the readings. Sometimes someone going inside just to take the reading may just touch the reference beam, and all the readings gets damaged. So all these kind of biases are there, which can occur in the settlement measurement. But these are the easier things to do. That's why I've just mentioned the settlement measurement first. And the more critical thing that most of the time we don't focus is the load measurement. So let's look how we measure the load in the pile. Now, there are two components that we can generally talk about. One is the hydraulic jack, and this is the hydraulic jack. How it works is that there is a pump containing oil in it, hydraulic oil in it. This is pumped, and this pump actually pumps hydraulic oil inside this cylinder. This cylinder tries to expand, and that goes back. This is how you apply load on the pile. So that's what a hydraulic jack is. But what is important to understand is that this load cell, it's the load measurement device. So although we often use this hydraulic jack for load measurement as well, but that is something which is not encouraged. And I'll show you in the next slide why it is not encouraged and what are the problems that are there. So what we need to clarify is that hydraulic jack, generally speaking, it's a load application device. And load cells are the load measurement devices which are there to be used commonly. Now, in order to understand this confusion more in a better way, let's look at the ASTM standard for the static pile load test and how it has evolved over the years. If we look deeply, we'll realize that the first ASTM standard was published back in 1981. But it was not until 2007 revision of the ASTM standard that ASTM made the use of the load cells mandatory. And that too only for the test greater than 100 tons. That's where it was the first time that ASTM actually made the use of the load cells mandatory. So there was a huge time lag in between. And during this time, it was always the hydraulic jacks which were used to measure the loads. That's the indirect measurement that we would do. And what has happened since is that the load cell in the recent revision in 2020 of the ASTM standard, they've made the use of the load cell mandatory for all the load tests. So whether it is a smaller load test or a larger load test, you have to use a load cell. Now, why this has been made mandatory and what are the benefits of doing this? So that's something that we'll look more in depth. So the problem with simply using the hydraulic system is that there are always some hydraulic system losses. There are friction losses in the fittings, and also there are calibration errors that are always there. And what would happen is that even when we calibrate those jacks, in a lab environment, this is a controlled environment where we calibrate those jacks. But when we put them in practice, practically in the field, what happens is that in the field, there is always some eccentricity of the cartilage that is there. And because of that eccentricity of the cartilage, the calibration that is done in the lab and the actual performance in the field, there is always a difference. And I'll show you more practical examples with some data in the next slide. So because of this eccentricity that is there in the lab and in the practical field, the results of the load measured through the hydraulic jack and the load cell, they often differ. And another thing is that the pressure gauge that you use, it has to be very reliable. The least we can do, and that's a common problem in the Pakistani construction industry, and that's something that we often ignore, is that these are the kind of pressure gauges that we use. At least what we can do is we can use digital pressure gauges. Why? Because a lot of times, although this hydraulic jack assembly is properly calibrated, but people fudge with these pressure gauges to change the value of the load. So that's something that if you are on the consultant side or if you are on the client side, having a load test done for your project, the least you can do is that you can have this manual pressure gauge replaced with a digital pressure gauge. So I think that's a bare minimum that change that we can do in the local industry. Now, again, to back these things up with some data, let's look why using a load cell is important. So let's look at this graph, for example. In this graph, you'd see that the x-axis shows the actual applied load. That's the actual or the true load, which was measured by the load cell. And the y-axis shows the error. Error means that's the difference between the true load and the load measured through the hydraulic jack. And you would see that the error in this test was around 15 to 20%. So it means that if you're not using the load cell and rather you're using a hydraulic jack for the measurement of the load, there is a possibility of error of up to 15 to 20%. And that's not a one-off thing. Let's look at another example, for example. So this is quite an interesting case. So there are two tests. One, say, is using a certain hydraulic jack. Let's say call it A, and there is an error of 15% in that. And there is another one which is say a hydraulic jack B, and that's only having an small error of 2.5%. So it would be quite obvious, and you would say, let's not use hydraulic jack A because it has a large error, and let's use a hydraulic jack B because it has a small error. So let's use that for the measurement of the load. So this problem is a jack specific problem and not anything else. But what if I tell you that both of these tests are performed by using the same jack? Both of these tests were performed by using the same jack and at two different piles, which are at the same piles, small distance apart, and just probably because of the eccentricity of the cartilage and some other unforeseen circumstances, the error in the load measurement was so significant. So that actually highlights why always using a load cell is important. So, and it's not only just because it's an ASTM recommendation, we need to understand why, what are the problems that can occur if we don't use the load cell. So then comes some local problems. So although I'm advocating the use of the load cell, but then there are some practical problems that come in the local industry. And what that problem is that the load cells that we use are commonly of, say, 1,000 tons capacity. But if you talk about the whole country, you would rarely find a calibration facility which would be able to calibrate in excess of maybe 150, 200 tons. You would go to maybe NED in Karachi, you'd probably find 500 tons capacity in, but it's sometimes not working. So the problem is if there is no calibration facility which can actually calibrate up to, say, 1,000 tons, how do you do that? How do you actually resolve this problem? So there are a couple of things which are important in this context. For example, you can always customize these assemblies. So for example, this is one project where we were tackling the same problem. So we just made a customized assembly to calibrate the load cell. There was a reference load cell. There was a hydraulic jack for application of the load. There was a reference load cell which was previously calibrated. And there is a load cell that is going to be calibrated now. But again, with all these things, it is important to understand this thing that ASTM suggests calibration every 6 months. unless otherwise specified. So that's the underlying part which we often miss and we often do not realize in our industry. So there are some practical constraints that are there. We need to realize that, okay, if our load cell, for example, is properly calibrated, and it has just been used maybe once in the last 6 months, and it has not been impacted to any jerks or impacts, and it was just stored in a clean environment, in a controlled environment. And after, say, in the 7th month, if the same load cell is to be used, then probably it will not be advisable. And ASTM just gives you that relaxation that you can actually have some tolerance in that. So that's something I think we need to be more practical, because when you talk about the projects that are being implemented over there, these kind of little things are often ignored. So we need to understand the practical realities of our industry as well, in my opinion. Now, another important aspect is that often while performing the test, we apply loading sequences. We apply loading and unloading cycles, how useful they are. Now, if we look at this angle, we realize that does this loading or unloading add any value to it? That's a question that I used to ask myself. You talk with people and you realize that some people would say probably this loading and unloading is gonna give you an idea about the cyclic loading behavior of the pile. But if you rationally think, you realize that it does not have anything to do with that. So if you dig deep, you'll realize that the origins of these loading and unloading cycles dates back a long, long time. In the early days, it was thought that this loading and unloading cycles show load distribution in the pile. But more precisely, in the previous times, the definition of the capacity that was used was that it is the load taken at 0.25 inch of net settlement after unloading. So you would just unload, and whatever is the unload cycle at which this net settlement is equal to 0.25 inch, that load would be your capacity of the pile. So that's the definition that used to be there several decades ago. Although our design standards and codes have evolved beyond that, and now in today's industry, this kind of definition of pile capacity does not exist, but still, what will happen is we still in many a times go for these loading and unloading cycles, which have absolutely no practical significance, in my opinion. Now, that's another thing that we often do is that we hold the load for a very long duration of time. Now, how does this benefit in a test? So, for example, let's look at this test. And what was done was these lines show the applied load, and this shows the settlement of the pile head. What is the benefit of holding the load from this 12 hours to this 48 hours interval? So that's like we have held the load for 36 hours, and you would see there is absolutely no change in the settlement. And that is something that any of us who would have actually executed a pile load test would have seen, that that's a very common scenario that we deal with. If there is no settlement, what is the benefit of holding the load for so long? Some people might say that it gives you an idea about the creep load, but then you'd ask more questions. How does it help you in creep load? And no one has an answer to that. So what the problems that occur in this case is that when you hold the load for a long duration of time, it is difficult to maintain the load for such a long time. So this green line shows the theoretical load that was to be applied. But this red line shows the actual load applied. So initially what happens is you applied the load, but what happened later on was the load bleeds and it goes down and down. And that's how this is probably the load that you are maintaining. So if you ask for unrealistic challenges in the field, it'll always cause these kind of problems. So probably holding the load for such a long duration of time does not add any real value. And in fact, if we go through the ASTM standard, the recent ASTM standard, they've made it much easier as well in this sense. Even the ASTM standard specifies that the quick method, that's now the standard method. And what that quick method does is, the quick method suggests that instead of maintaining the load for a long duration of time, what is better is you apply smaller load increments. You apply smaller load increments, hold them for a shorter duration of time, and then move to the next one. Hold that for the same duration of time and then move to the next one. And that's what the current ASTM standard also suggests. So that actually shows you that holding the load for a long duration of time does not add any real value to the test. And to emphasize on this more, just look at this another example. You see, another practical thing what happens is that this is the reading, the last reading that was taken at 10 p.m. And after that, that was the load which was supposed to be held the entire night. And if you look at the actual trend of the applied load, you would see that probably the person performing the test slept. And that's why the load fell down. And probably in the morning he woke up, he turned the pump on again, and that's why the load went up. And again, he was just trying to maintain the load for this duration of time, and it was such a challenge. And actually, this problem was resolved maybe the next evening ultimately. So our objective is to have a really high quality test. And why it is important to have a good understanding of pile behavior. In our reports, we would put in this blue line, whereas the actual load that was applied on the pile was this red line. And you as a designer, someone taking a decision, would not know about this red line. He would just base his decision on this blue line. So probably it's better to actually update our specifications to meet the modern standards, which actually suggest you to apply, to use the quick method, apply smaller load increments, and apply it for a shorter duration of time. So that's something that can help. But even if you have to apply for longer duration of time, what's the way to do that? There are systems that are available internationally, although it's not common in Pakistan, but these are the kind of systems that are available which can assure automatic load application. So what happens is that if the load starts dropping up, the system kicks in and it turns the pump on automatically, it increases the pressure, and the pressure is maintained. So that's something that can be done. Or the other way is that you can babysit the load, as you can see here. So there is a digital pressure gauge, where the engineer can actually notice the load. There is another digital pressure gauge which is connected to the system for automatic data logging. And you are actually controlling and babysitting the load and managing it. But probably a better way is, if you're not able to do that, just get some automatic load application system, and that will solve all your problems. So we talked about the reaction assembly, and I said I'll talk more about the different kinds of reaction assemblies that we have. So we only know about this cartilage type reaction assembly, where we either put concrete blocks on top or we put some sandbags sometimes, but it has its challenges. This is quite unsafe. Many of us who are practically doing this kind of thing in the industry would have seen a lot of safety hazards to that. Another challenge is that the maximum load that you can apply is limited. For example, this cartilage is for around 1,400 tons of load. The biggest that I have seen probably internationally would probably be of 4,000 tons. So the maximum test load is limited, and that actually restricts the designer as well, that if he wants to design a pile, if he wants to economize the system, and if he wants to design a pile which can carry a much, much larger load, or if the trial strata is competent, he cannot design a pile that can carry maybe 7,000 tons of load, because he know it will not be possible to actually test it. So it also requires a lot of space. So, and a strong foundations are required over here as well. So all these problems are there with the cartilage assembly. So what are the alternatives? There are other alternatives that are there as well. For example, this is an assembly for the 6,000 ton load test that was done. And that's done through reaction piles. What you do is around the main pile, you do reaction piles. The main pile is in compression, the load is being pushed down, and the reaction piles are in tension and they are being pulled up. So that's how you can actually do it. this kind of an assembly becomes a little difficult as the diameter of the pile keeps on increasing, but that still solves a lot of problems. And that's actually more safe and more time saving as well. And sometimes it's more economical as well. And actually, this is just a practical example that this is not only something that can be done worldwide. That's, for example, a 2,000-ton pile load test that we were able to do recently in Pakistan as well. So that's something that's possible even with the current resources in the current environment as well. Another option is to go for a crown anchor assembly. That's also something that can be of a lot of benefit. So there is a crown type arrangement that is put on top of the pile. Same hydraulic jacks are placed here, and then you have the anchors which are surrounding it. So that's how the jack tries to expand. The anchors provide the required tension to make the system stable. And this is fairly good for congested spaces. It's quite time saving as well. But there are challenges. The maximum test load is limited to a certain limit. It depends upon the capacity of the crown and also on the surrounding soil. It has to be competent enough to provide enough tension to the ground anchors. But this is also a possibility that can be utilized. And you can see if you want to test the working piles, for example, for using the crown anchor arrangement. So this is a congested working pile arrangement where you have all the working piles, and these are the tests which are using the crown anchors, which are done in the same environment. So even in the congested spaces, this crown anchor arrangement can provide you a lot of benefits. So you've done the test now. We have seen what are the different possibilities of performing the test. Now, how do we interpret the results? So that's the next thing. So as we already discussed, we get the load settlement curve. But for example, you have the two graphs, both have one having a large movement, one having a small movement, both showing almost the same kind of load. How would you determine the capacity? That's the actually more tricky part. The common answer that you'd get is that there are many interpretation methods that we can apply. But before going that, let's look at what is the meaning of capacity when we talk about capacity in civil design. What do we mean by that? Now, looking at the civil engineering design, the capacity means it's the load at which the material fails. And we very commonly understand about the capacity of the steel bars. That's the load at which they fail. Similarly, for the compression test of the concrete cylinders, that's the load at which the cylinder fails. So that's very easy to establish that what is the capacity of the steel bar or the concrete cylinder. But how do we define the failure in case of piles? As we already said, it's easy to define the failure in case of steel or concrete, but how do we define the failure in case of piles? In case of piles, that's probably how we define the failure. You perform the load test, you have the load settlement curve, and in the load settlement curve, wherever you see the pile starts plunging, you would call that this is my failure load, because this is the load at which the pile starts to settle down without taking any further load. So that's something that you would call as the failure point. So it's easy. But that's not practically the case, because this kind of load settlement graph is a rarity. You'd not always find this kind of a load settlement graph. What is more common is probably a graph like this. Now, in this graph, if you'd see, you are increasing the load and you have the movement. There is no distinct plunging that you are seeing here. So if you're not seeing any distinct plunging, how do you determine the capacity? There are methods that many people are already aware of. You apply the Davison's offset limit method. That's something which is very commonly used. So by applying the Davison's offset limit method, you apply the initial tangent, you draw an offset to it, and where this offset cuts the graph, the load settlement curve, you call this as the pile capacity. But is this the only method that you use? No, because there are many other methods that are there to determine the capacity. For example, I've written just names of some of those methods which can be applied for the determination of the pile capacity. So the next question would be, okay, there are so many different methods, but the capacity that you determine from all these methods must be similar. So it does not make any difference which method you use. you'll ultimately end up with a reliable value of the pile capacity. That's something that how we generally would think. But that's not again the case practically. What I mean to say is that, for example, in this graph, if you see the pile capacity that you determine by using the Davidson's method, it's 181 tons, and it goes as high as 235 tons if you apply the Chin's approach and all this scatter that is there. Now, it is important to understand is at a pile having an overall capacity of say 200 tons, there is a scatter of almost more than 50 tons, what means is that there is a possibility of scatter of around 25% between any two people who are determining the capacity. So it is such a large scatter. We are talking about precise numbers, and if there is a difference of opinion of 25%, it's a large number in any kind of design. And this is not a one-off example. You'd find many other examples. For example, you pick up the second example and you'd see in this load settlement curve, the Davison is giving a capacity of probably 314 kips, and you can go up to 570 kips by using the Fuller and Hoy method. And if you go for Chin method, that's in excess of 880. So this is almost double of the Davison, and Chin is maybe more than 3 times of that. So selection of capacity is again a very tricky subject to see. And what happens worldwide is in the developed world, what they do is they do pile prediction competitions, for example. What it means is this is one such competition that was organized back in Sweden in 2018. And what they did was they casted a test pile and they gave all the parameters of the test pile to the participants of the competition, and they ask them to make their prediction of the pile behavior. So they are going to perform the pile load test, but before the pile load test, they gave all the input data to the participants and they asked them to predict the behavior of the pile that they have. And you would see everyone would come up, all these blue lines would be the predictions made by different participants who themselves were quite expert in the discipline. And this red line shows the actual tests. So you can see our understanding of the pile behavior and the load settlement behavior. There's no consistent understanding that exists even worldwide. Worldwide, there is a huge scatter that is there. And that's again not a one-off event. You'd see that there was another prediction event that was actually organized by ISSMGE, and you'd see all these light lines show the predicted behavior, whereas this red line shows the actual behavior. And again, you can see that there's a huge scatter between the understanding and the actual pile behavior. So it's very different it's very difficult to have a good understanding, and there's a huge scatter that exists even worldwide in understanding the pile behavior. Now, and that's not only in the load settlement curve. Even if you talk about the pile capacity, so once they performed the test, they got this red line, then they gave the same red line, the actual load settlement response of the pile to the participants, and they asked them a follow-up question. They asked them, what is your estimation of the pile capacity? And you'd see when they asked them, there are again a huge scatter of responses from all the participants. Some participants thought the pile capacity should be somewhat around 6,000 kilonewtons, and there were large number of values which were suggesting a pile capacity in excess of 8,000. So you can again see even there is a lack of understanding or lack of coherence on the understanding of the pile capacity as well. So very quickly, let's talk about the geotechnical capacity of the piles. When we talk about the capacity of the piles, it composes of 2 components. There is the ultimate shaft resistance and the tip resistance. The shaft resistance derived by the shaft, the toe resistance derived by the toe. What we generally do in our normal design practices is we apply a certain factor of safeties on the shaft and on the toe. And whatever is the answer, we call it as the allowable load. We call it that this is the load at which we can allow. And the important point that I want to make here is that when we are predicting the capacity of the pile, what we do is we determine the shaft resistance and the toe resistance separately. And when we are validating the behavior, for the validation of the behavior, when we perform the pilot test, we get a single load settlement response. In this single load settlement response, there is no way to separate this shaft resistance and toe resistance from this graph. There is no way you can do that reliably. There are some approaches that exist. For example, one such approach that you can apply, and from that approach, you can get that this is the shaft response and this is the toe response. These are empirical approaches proposed by some researchers. But one may again argue that is this distribution of shaft and the toe accurate, or this distribution of the shaft and the toe accurate? You can see in this case, probably the shaft resistance reached its peak, then it started to strain, whereas the toe kept on taking the load. And in the other case, the majority of the load is being taken by the shaft, and almost no or a negligible load is taken by the toe. So we started up from this equation and had separate shaft and toe resistance. But when we perform the pilot test, we end up with a single number at the top of the pile head. We cannot separate these two out. And if we cannot separate these two out, we will be unable to understand the behavior of the pile. That's what our real goal is. So that's the big challenge actually that we come in. So, the point I'm trying to make is that the head load settlement curve does not provide the full picture. So what we can do in this case is, we need to put some sensors or instruments in the pile, and by doing that, we can actually separate these two out, and we can have a better understanding of the pile behavior. And if we have a better understanding of the pile behavior, that's the only way we can design more economical and more safe pile foundation systems. So that's pretty much the end of the first part. So, Tahir Saab, if you think there are some questions and we can have a break of say 5 to 10 minutes to answer those questions, I'm okay. Or if you suggest we continue, we can have that in the end as well.
Well, we had only one question from GEC Hober, that is Pervez Saab. He asked how much was the maximum load applied in the pile load test by you in the park? Maybe you referred to some tests. So he just wanted to know how much was the maximum load. Though Shia has already answered his question, I mean, how much load she has applied already. But if you have the figure, please provide him how much load was applied.
So probably what Nushai Saab is referring is to this slide probably. So that's the test which we did for 2000 tons. And I know from the global standards, it's a very small test, but from the Pakistani standards, it's a large test actually. So that's the answer to his question. So it's 2000 tons was the total test load.
Well, now there is, I don't see any other question, but I just, for my curiosity, I just wanted to ask, discuss with you one side point, that when we are doing the pile load test, whether it is in tension or is it in compression, what do you think about the ASTM codes or the British codes, which suggest that the distance between the supporting beam should be 5 times the diameter of the pile, and some suggest 3 times the diameter of the pile? Do you want to comment on it?
Yeah, I think it's a very interesting and a practical point. To be honest, my understanding would be that the ASTM or the British standard, what it suggests is the maximum thresholds, because that they have to generalize things to fit in the context that can be applied in the entire world. My question would be that what are the soils we are talking about? If we are talking about soft ground conditions, maybe soft clays or something, yes, in that case, I might personally be interested to even increase the spacing to 6 times the diameter. But if we are talking about rather stable grounds, I personally might even be okay by decreasing that distance. What I would probably do is I may run some FEM to see the behavior, how in this strata, how much the lateral spread of the stress would be, and accordingly I would decide. But if I talk about, for example, from the Pakistani context, one may argue that uh, in the same project, we would, while following the ASHTO guidelines, we would say that there would be a group efficiency factor of 1 for a 4 times diameter center to center spacing. And for the same project, when we talk about reaction piles, for example, someone may ask that the ASTM suggests 5 times clear spacing, not even the center to center spacing. ASTM asks 5 times clear spacing. So there is a mismatch, in my opinion. So I personally think that we have to look at things from the more practical angle, and in more stable soils, you should be able to reduce the spacing.
Thank you for such an elaborate answer, and most of stuff you have expressed in your response. I too agree with it. So we don't have any further questions. You can continue, but I would again request all the audience that if you still have any questions which will come in your mind later, you can just type your questions in the chat box, and I'll be there to read them. Dr. Saab, continue, please.
Okay, thank you very much. So, so this is where we finished. We saw that we designed the piles by segregating the skin friction and the toe resistance. But when we talked about understanding the pile behavior, we only relied on the load settlement curve, which is the head settlement curve. And when we talk about the head settlement curve, we don't know what is happening inside the pile. And that's why we said it is important to have instrumentation there. So how do you do instrumentation, and what's the benefit of it? How do you do it? So I'm just going to make it very easy and very simple, just trying to give some basics and fundamentals about it. So what instruments that we use are, the first one is the load cell, and we have talked a lot about it already. We put some load cells at the top so that all the load is digitally being measured, fed into a system. So that's the load cell that we use. We use the extensometers in the pile. So these extensometers are strategically placed within the pile. And what they do is they are able to measure the settlement or the movement of the pile at the locations where they are installed. What I mean by that is that previously we were only measuring the head settlement. But if we install this kind of telltale extensometer at the mid depth or at the toe, we will be able to see the movements at the mid depth and at the toe as well. Then finally, we have the strain gauges, and these strain gauges again are located at different depths within the pile. What they do is they give you the strains inside the pile, and if you know the strain inside the pile, you will be able to convert this strain into the load. So these strain gauges give you the strains inside the pile, and you are able to convert it into the load by simply using the mathematical expressions. Although there is quite a lot of complication to it, but I'm not going into that detail. I'm just going to try and keep it very, very simple and basic for that. So that's how you install the strain gauges. So what happens is when you have applied the strain gauges, these strain gauges, whatever location where you have applied, these actually start giving you the response at those locations. And what I mean by that is you can pretty much start getting the spring stiffness at those locations. And those people who are more from the structural side, they would have a better idea about this, because this is how they actually model their piles in their structural design software. So this is the key thing that they are actually looking at. They're looking at the Winkler spring stiffnesses. So generally speaking, we geotechnical engineers are providing those spring stiffnesses based upon the empirical method. So if we install these sensors, you're able to get the actual pile response at these locations. You are able to get the actual spring stiffness response at each of these locations, and not only each of these locations along the skin, but also at the toe as well. So that's something that you'll get. These graphs that you get along the pile length are something we call as the TZ curves, and the graphs that you get near the toe is something that you typically call as the QZ curves. And this is something, the TZ curves and the QZ curves are something which are of most interest for the structural engineers. And probably from this, you would have got an idea how how we can understand the pile behavior in this way. And from these graphs, we can ultimately plot the load transfer curves. Now, what I mean by the load transfer curves is that you can see that as we apply the load, as we increase the applied load, we are able to see how this load is being transferred at different depths in the pile. Let me give you an example. For example, this is the first loading increment, second loading increment, the third loading increment, and the final loading increment. So at the final loading increment, suppose this 7,200 tons of load or kilonewtons of load is applied. These sensors would tell us out of this 7,200 kilonewtons of load, probably around 7,000 kilonewtons of load was transferred to this depth 4 meter. And probably a 6,500 kilonewtons of load was transferred to a depth of 12 meters. And in the same way, by following the same procedure, we can get a clear idea of how much load was transferred to the toe. So that's what you can actually get from this. So it can clearly tell you how much of the load is being carried by the skin and how much load is being carried by the toe. So that's the benefit of this kind of instrumentation. And I'll just skip through that. And this is again an example of the load transfer curves that we were talking about. So the load transfer curves would actually, you can see these two graphs for two different piles. On the left side, you can see there is a very small mobilization of the toe. And that is something that is somehow evident from the head load settlement curve as well. You can see there is no plunging here. But for the second pile, you can notice that there is a significant portion of the load is carried by the pile toe. And that is also evident somehow from the head settlement curve that there is a plunging of the pile over here as well. So you can probably say that the toe capacity was reasonably mobilized on the example on the right side compared to the left side. So let me give you a couple of quick examples, quick case studies. For example, this is a multi-story apartment building project that we did in Islamabad. So it was an interesting project. Half of the project was on fill, half of the project site was on cutting. It was on the top of the hill, and at the toe of the hill, there was an old nala that used to flow. So this just gives you an idea about the typical cross section, but this so there is quite a significant thickness of fill that is there, that is available there. So previously there was two pile tests. There were two load tests that were to be performed. So there was a test pile A, and they designed it to have an ultimate load carrying capacity of 800 tons. So just dividing with a factor of safety, they said the allowable load carrying capacity would be of 330 tons. Similarly, there was another pile which was planned to have a diameter of 0.6 meter and a length of 45 meters. We analyzed the problem ourselves and we realized that probably if our objective is to carry a load of around 300 tons, probably we can try by giving a 0.6 meter dia pile with a 30 meter of length, and we tested it to 1,000 tons of load. Now, what is important here to understand is that you need to just compare this instrumented pile load test with this test of TPB. Both have the same diameter, same lithology, one having a length of 45 meters, the other having a length of 30 meters. So generally speaking, if this pile is having an ultimate load carrying capacity of 650 tons, this pile should have a capacity of much smaller than 650 tons. It should settle much quickly compared to this pile. So let's look on the next slide how the actual behavior of the instrumented load test went. You need to remember this number of 650 tons. The pile, our test pile should plunge much before 650 tons. So we applied we decided the scheme, we have installed some sensors on it, and when this is just an image of what kind of assembly we use over there. And then this actually shows you the load settlement graph. You look at this, focus on this load settlement graph, only the heads load settlement graph, and you would realize that we were talking about that this pile, which is of a much smaller length than 45 meters, should actually plunge at 650 tons approximately. But this is taking much higher load without showing any sign of plunging. So what is the reason? It means that the previously assumed pile capacities were significantly smaller than what the actual strength of the soil is. If we have not put in sensors, we are unable to get an answer to this question. So by putting in sensors, this is able to give us an answer. And this is the load transfer curve that I was talking about earlier. This actually tells us that almost negligible or no load was transferred to the pile toe. Almost all the load was carried by the skin. And if you look, there is almost no load which was transferred to the toe of the pile. So, and not only this, the majority of the load was taken by 50-foot length of the pile. And even underneath that, the load transfer was almost negligible. So this information that maybe if you would not have given this additional 30 feet length, that would have been enough maybe. Looking at another case history, for example, this is an apartment building project in Karachi. The test pile was around 137 feet. The actual pile was casted to be around 103 feet. We put sensors at different locations again, and looking at the load settlement response of this pile, we realized that at the maximum test load that was anticipated, there was a very small settlement. There was a very small settlement of only around 6 mm of settlement that was there. Now, under the normal circumstances, if this pile was not instrumented, probably you could not have done anything other than just accepting that this length of 103 feet is okay. You can go ahead with this. But just because you had sensors in it, you can clearly see the response, and you can see that this is the response of strain gauge 1, which is at the top, the strain gauge number 2, which is here, and you can see as you go down at strain gauge 3, there is a much smaller strain at this level. And at strain gauge 4 and 5, probably no load was transferred at strain gauge number 4 and 5. And that actually gives you an idea that all this length is probably redundant, and you can actually avoid providing this length because no load was transferred to this depth. And that is something which is visible again from the load transfer curve as well. You look at the load transfer curve and you see that at strain gauge level 4 and 5, there was almost no load was transferred. So what we did was, we plotted this kind of graphs. This is the mobilized skin friction versus the depth. And if you divide it into different layers, now these are the actual skin friction that were mobilized in the pile. Now, this is important to understand, because previously when you are designing it as a designer, these are the numbers of the unit skin friction that we determine by applying any of the theories that are mentioned in the literature, whether it be alpha method, beta method, or any other approaches that are given. But now, because of these instrumentation, you are able to actually see how much skin friction is mobilized there. And if you are able to see that, actually, you can actually work out what is the total length of the pile that is required, and you can actually work out that this 100 feet of length that we have provided is probably not required, and you can actually provide a smaller length of the pile. And in this project, we were actually ultimately able to reduce the length of the pile to around 78 feet by using the same kind of approach. Now, moving to the last part of this lecture, we talk about a new innovation technique And that's the bidirectional pile load test. And that's something which is again pretty common. And I'm sure our friend from China who has joined in would probably share something on that as well. So let me give you a brief introduction about what this is about. The bidirectional, it's also known as the O-cell. This is an interesting technique which was developed back in the 1980s by Professor Georg Osterberg. He established a company later on in the 1990s, and that's the same company which was later acquired by Fugro and later became the Fugro load test, and they became the worldwide leaders in this technology. So just to give you a quick perspective of what this test is about, what you do is you don't need any reaction assembly on top of this. All you need is the hydraulic jack that is at the top. You actually move those hydraulic jacks within the pile. So these hydraulic jacks are moved inside the pile, and these are specially designed hydraulic jacks. These are not the traditional hydraulic jacks that we use for the static pile load test. These are specially designed hydraulic jacks, and they're moved inside the pile. And then what you do is you take these pressure lines outside, you put all the instrumentation and everything the same way as you have done, and then you pressurize those jacks by using those pressure lines. And what happens is that these jacks inside, they try to expand. And when they try to expand, they push the pile upward and downward. So by doing this, you are able to actually see the same kind of pile behavior. I'll explain more of that in the next slides. So this is just to give you an idea how these jacks look like. They're just installed inside the cage, inserted into the pile. And once you have installed that and you have actually tested this, so this is the cell that is there. You apply the pressure from that, you expand it, and once you expand it, the load settlement graph that we are typically able to see, we get this kind of a load settlement graph as you can see here. Now this kind of a butterfly curve, which we call it, this shows the upward movement of the pile, and this shows the downward movement of the pile. So this is, you can say, somehow reflecting the toe behavior, and this upper part is somehow reflecting the skin behavior of the pile. Now, going back to the same question, just by doing this, we've been able to separate the behavior of the skin and the toe of the pile. That is, as we discussed earlier, is important to understand the behavior of the pile, and that can be used then ultimately in your designs. And not only this, there are approaches which are available, and they are well-recognized approaches which you can use to convert this butterfly curve into a conventional load settlement curve that we are more comfortable seeing. So you can convert this butterfly curve easily into the top-down load settlement curve as well. Now, so I'll just quickly skip that, and I'll just quickly move to save time. I'll show you some of the benefits of the bidirectional static load testing. So there are four major benefits. You can save space. All the safety concerns that we have talked about are gone. The maximum test load, it's not restricted, and you can save time as well. This is something that we are more used to seeing, that as with more urbanization, we are having to perform these load tests in dense congested environments. I personally remember working during the days of the Orange Line Metro train project, and it was a huge hassle. It was a very tough thing to actually find a place where a test pile can be casted and ultimately a huge cartilage can be erected for the performance of the load test. Now compare all this space with just a small space that is required around the pile that you can do by using this bidirectional pile load testing. And also, if you are to test, for example, in offshore and these kind of places, it again is a huge challenge and a huge cost, and it can save you on the cost as well. And talking about the safety and the maximum load, we have seen these kind of failures not only in Pakistan but abroad as well. And making a cartilage or even for the reaction pile, a small failure can lead to a catastrophe. A lot of people have lost their lives in that, and it can actually delay your project as well. And the other big challenge is that the maximum test load is limited. The maximum test load is restricted. We, as I previously mentioned in our talk, that are generally we are generally comfortable seeing loads of the order of maybe 500 tons, 1,000 tons, 1,500 tons, or a maximum of 2,000 tons in the local industry. But if you want to go to a higher load, that's not possible with these conventional assemblies. But when you talk about the bidirectional pile load testing, anything is the limit. So you can see this is just some data that I found. Even in 2010, probably it was a 36,000 tons load test that was conducted. And you can imagine the possibilities that are there. And I'm sure probably 15 years have passed from 2010, much larger tests would already be done than this. So this limit is also eradicated if you do that. And we also know that time is also a big challenge generally in Pakistan in any project, but more so in government fast track projects. Time is always a challenge. So it's a very quick method. You can do it very quickly. You can save a lot of time. It's a very conservative estimate that I have given here. Because you see, even in these 33 days, the majority of the time is that is to wait and wait for the concrete to achieve 28 days strength. But if we can, just for that test pile, if we can use an early strength concrete, we can probably bring this time down maybe to 10-ish days or something. So you can save a lot of time just by using the bidirectional pile load testing as well. So that's pretty much it. Now, just to give you some concluding remarks on this, I've tried sharing some practical insights from the hands-on experiences in the pile testing industry. And I've tried to emphasize that just by performing a static pile load test where you measure the head movement only, that does not give you the full picture. That does not give you the full idea about the behavior of the pile. And for that reason, you have to invest a little bit more at the testing stage. And if you invest more at the testing stage, that can actually pay you back big time in the pile, in the entire lifespan of the project, in the construction working pile stage. And in this context, the instrumented and the bidirectional pile testing can benefit you a lot in this context. This by doing all these, we can go have more reliable testing, and if we have more reliable testing, that can actually lead to more safer and more optimized designs. That's the end goal actually, and that's not possible again without understanding the full behavior of the test piles. And many times I've seen on the projects, people are sometimes just concerned by just checking a box that pile test was done. Without realizing the significance of this thing, that the whole project's sanctity sometimes lies on just one good test being done. So that's why I think it's important to realize its importance and focus more on that. So that's about it from my end. Thank you very much for your attention. I'd be happy to answer your questions.
Thank you very much, Doctor. We have one question from Ghulam Rasool. He's probably working in Saudi Arabia and with some geotechnical company. And his question is regarding BDSLT. Ghulam Rasool Sahab, I think most of the question, what you have asked, it has been answered by our speaker in detail. So I will just read out your question. If there is anything the speaker can add, I would be happy to listen to it. I'm reading this question for you. which test method is more efficient, the conventional static load test or the bidirectional static load test, BDSLT, using an O cell placed inside the pile? A little insight is requested, commonly conducting in KSA. Would you like to add anything, Dr. Saab, to already what we have said?
So I think that's we've already answered that question in a lot of detail. I think at least doing a bidirectional pilot test gives you a benefit that it enables you to segregate the skin friction and the toe resistance. So that's a big benefit that you get from the bidirectional load testing. But ultimately, what is there is that one needs to understand that even by segregating that, how to get the benefit from that information and to actually use it in the design. So that's the second stage. That's something probably for some time later we can talk about that.
Yeah, and isn't it one more thing that the heavy beams and for this conventional type of load test which we are doing, the heavy beams and the heavy equipment which we have to mobilize, at least in this BDS SLT, you get some advantage there that you don't have to mobilize such a heavy equipment, isn't it?
Yeah, definitely. You save a lot of cost this way, but I think it's a balance. What my working is, cost wise, you pretty much end up being at the same place. In some projects, for example, if there are more tests at the same location, still moving the blocks might end up being cheaper. But it's not necessary. But yes, because the jacks here are sacrificial. They are going to be inside and they're not going to come out. So it's about a compromise. But I think if we talk more from the angle of the benefit of the project, you get more information from BDSLT, and that's the real benefit of it.
Okay, we have this is the last question, and let me see if we have any more questions. You see, I'm going to read the last question, and after that, as Dr. Sabri said, I'll give a minute or so to Miss Wang. If she wants to say anything on BDSLT, then I'll give her a minute or so. So, Dr. Saab, the last question is from Parvez Mushahi Saab. Dr. Irfan Saab, please also mention subsurface profile of Karachi site. I think it could be conglomerate type profile.
Yeah, I think it's a very valid question. Just for the because of shortage of time, I did not go into that detail. So there was no conglomerate there. There was clay, pretty much soft to stiff clay later on at a depth. But we ended up having our toe in limestone there. So that was the strata. But significant portion of the pile was in limestone. So probably that was the reason that even at shallower depth, majority of the load was taken and it was not transferred to the toe. So we got pretty good skin friction from there.
Okay, thank you. So the question answer hour is over. Shia, I'm giving you 1 minute if you want to speak. Let me tell the audience who is Shia. Shia is involved in BDSLT in the equipment, and she has quite a detailed information she's quite knowledgeable, I should say, on BDSLT, but we don't have that much of time. So I can give her 1 minute. If she wants to speak anything, she can do it now. Shia, the floor is yours.
Hi, hello everyone. I'm Shine from Ugan Group. We have do the pill test, especially the OCL test for over 20 years. So now we are the largest and the most professional company for the OCL in China. And thank you so much for this invitation from Mr. Tahir Satan. I have learned a lot from here. And for the question from GEC, I will share this case study and that to Mr. Tahir Satan and share all this to you. Okay, is that okay? So we can learn together and know how to do the OCL and to do the BDST test. That's all. Thank you.
Thank you, Shia. Thank you very much. And that brings us to the conclusion of this webinar. And Dr. Saab, thank you very much for sharing your insights on pile load testing with such a clarity and such eloquence. I really appreciate your depth of knowledge and fluent delivery undoubtedly enriched our understanding. So I'm confident that today our audience leaves today better informed and inspired by the knowledge which you have given in this in your lecture, and I hope it will help our audience to apply what you have said in the field also. Thank you very much, Dr. Saab. I always appreciate your coming to this forum, Pakistan Society of Civil Engineers, and you have been a regular speaker from our forum. Thank you. So
Thank you very much.
now,
Thank you.
I have to make some announcements. Let me read out some what I have to say in the end. Yeah, the next lecture is on 15th November 2025. The topic is innovative tools for enhancing engineering education, and our speaker would be Dr. Naveed Anwar. He would be speaking from AIT University in Bangkok. Certificates for today can be collected from Monday, 27th October onwards from 14A1 Block P, Model Town Extension, Lahore. And before coming, if you want to check whether the certificate is ready or not, you can contact Ahmad Akram. His cell number is 0347 562 5111. So, Dr. Saab, your certificate or your shield, inshallah, will reach you at your address, office, or home, wherever you will desire. Sadia will contact you in this regard. So, ladies and gentlemen, thank you very much. And before I finally conclude, my thanks to my coordinators, Mrs. Sadia Naveed, and my IT person, Hasnan. So thank you very much. God bless you all. I will see you on 15th November. Thank you.